It's just a review of midpoint. So what we're going to be doing is taking the midpoints of all of our subintervals here to calculate an average of the area underneath our curve. So we have our integral, and we can plug this in our calculator and find the exact value. But what happens if we don't have an antiderivative, or we're dealing with data that doesn't have a function? So then we can't use our little tricks and stuff that we've learned for integrals. So we have to go back and use our different rules. So we're going to be using midpoint. We're going to be using trapezoidal rule, and we're going to be using Simpson's rule. We also have left and right that you can go back and review as well. But we're going to be starting here with midpoint. So back to our problem. So we're going to take this little function, and I've already got it graphed here. So this is the graph of x squared over 1 plus x squared, x to the fourth. So to get this picture in our calculator, you would plug this in, and then you go to your window, and you would start with our interval. So we're going from 0 to 4. Those are our starting and stopping points, our A and B. And you want to hit zoom 0 to fit it. And then that way we're just going to get the graph that we want. And so now obviously I've taken this picture and I've stretched it out like this. This is through Desmos. And there's the link right there if you want to do your Desmos graphs the same way. All right, so we've got our picture. We've got it drawn. And so what we're going to do now is cut it into 4 subintervals. So to do that, we need to know what our change in x is. So it's always the b minus a over n. But really just think about what it is. We want to find the total range here, our total width of our entire part that we're looking for. All the subintervals. So the entire interval. So we have 4, take away 0. So that would be a width of 4. Well, how many pieces are we cutting it into? Well, 4 subintervals. So that means each width needs to be 1. That's all our delta x is our width. So we're going to have a width of 1. So if we start at 0 and we end at 4 and we put 3 lines in there, cutting it into 4 parts, we know that our first one would be 1, and then 2, and then 3, and then 4, because our delta x is equal to 1. So now what we need to do is find the midpoint. And you can just look at it a lot of times and tell exactly what number it is. So what's the point in the middle? Yes, it's a half, so 0.5. But if you don't, it's just midpoint formula. So if you take the starting point of that subinterval and the ending point of that subinterval, and you add them together and divide by 2, it's the average. So if you want to find that point, all you're doing is 0 plus 1 divided by 2 is 0.5. And so if you wanted to find this x value, this would be 1 plus 2 divided by 2. So that's 3 divided by 2 is 1.5, and so on. But we need these values here to tell us our heights. So we're making little rectangles. And those x values are going to give us the height. So all we have to do is plug them in to our function. Well, what is our function? It's whatever's inside. You see, that's our f of x. So our f of x here is equal to x squared over 1 plus x to the fourth. So what we need to do now is if we plug in 0.5 into here, into all of this, it tells us the height. We plug in 1.5, it tells us the height. 2.5, it tells us the height. 3.5, it tells us the height. Okay, so I'm going to show you a couple ways to figure these out, but what we need is we need f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5, and then we multiply this entire thing by the height, or the width, I mean. The width here is our delta x, which is 1. So what's really happening is if you think about our first rectangle here, right here, that first one, draw it over here, it has a width of 1 and a height of f of 0.5. And then our next one would have a width of 1 and a height of f of 1.5. So it's a little bit taller. F of 1.5 with a width of 1. And then this one's even smaller, but it's a width of 1 and a height. So they all have a width of 1. So if we were going to add all of these up, it'd be length times width, right? This is just 1 times f of 0.5. This is 1 times f of. They're all being multiplied by the width. So that's where your delta x comes in front, right in front here. So it's always going to be delta x times all of your little points, all the way to the end. So all you have to do is find the heights at the midpoint, add them all up, and then multiply with 1. The other way to look at it is if you were to take this height and this height and this height and this height, and we just stack them on top of each other, they would look like this. Oops, that's a really small one, the last one, huh? tiny one like this. So we would have a f of 0.5, and then an f of 1.5, and then an f of 2.5, and then an f of 3.5. And what's their width? 1. So if we add all of these together, they tell us the total height of that one rectangle they all make with a width of 1. So long story short, you take the midpoint, plug it in to your function, and it tells you the height of each of your rectangles. So if you add those up, multiplying by 1, it tells you the area that's approximated by all of these rectangles. You can see that some are overshooting it, some are under, over, under, over, under, and then we'll see what we get. So the first way is to just actually plug these into your calculator and write them all down. So we've already got our graph. So if you just go trace, and then our first x-coordinate is 0.5, you get 4/17. So you write that down. And you go back into your calculator and you do the same thing, trace 1.5, and you write it down, 36/97. Now this is going to take a while, and you can tell the nice thing about doing it this way though is you're actually seeing that that's the height at that point. It's right in the midpoint, it's giving the height. Quicker way to do it though is you go to your table, and our first point that we're starting at here is 0. So we want our first point to be 0. Right? And then our width here is 0.5. So our first point is going to be 0.5 away, right? So our first point is actually at 0.5. So 0.5. And then how far is it from 0.5 to 1.5? It's 1 unit away. Now you could also start at 0 and just do 0.5s, and it'll give you all those points for 1.5, 2.5, and 3.5. It works the same way. But what we're doing here is if you use your table function, see, it spits them out. So the next is 100/641. You don't have to keep hitting trace. It's a one-time thing. And then 196/2417. And then we add all of these up in the calculator, and it'll see what we get. Now remember, I told you there's another way of doing it. So you can use the trace in the table to get the points. There is one more other way. So 4 divided by 17. And then we plug it all in and then multiply it by 1, which won't change anything. So we get 0.8435. So that's our approximation of this integral. And you can use the Desmos. They're also on my website for each of these functions, but you can see that it'll tell you the answer. So you can go up here and actually input the function, put the a, put the b, and then the n. 0.5 is midpoint, and the number of n, and it will tell you the answer. It also gives you the integral to see how off you are. So you can see that our estimate here is actually going to be under. It won't be actually at the top here. It's not going to go over. So we are actually underestimating this by, so if we took this one and subtracted this one, right, then we are under by 0.02. So our error here would be positive because we'd have to actually add to this to make this one. So we're under. Now I did say I'd show you another method, and that's for the calculator. So in your calculator, as long as you have your y already created, then under VARS, your vars, you go to yvars, your variables, and you see function, and there's y1. So it'll bring it up, and then you put parentheses and your first input, so 0.5. So that would represent f of 0.5. And then you push plus, vars, scroll back over, hit enter, and you're a lot quicker than I am when I do this. And then we put in 1.5, and we just keep doing this. 2.5 with parentheses, of course. And then one more left. There we go. So it's vars, yvars, and then function. All right, so now if I hit enter, did I forget a parenthesis there? I hit enter. Yep, forgot a parenthesis right there. So you got to make sure everything, so it's good that we make little mistakes here. Show it. Make sure they're all parentheses around each one, or it's not going to know what's going on. So we have parentheses around 0.5, 1.5, 2.5, and of course 3.5, and there it is. There's our port 0.8435. So you could just do y1 and then the inputs. And that's basically what's going to be happening with a lot of these problems. You just have to put the inputs. So you just have to know what functions you're using and the inputs. But there we go. So that is our approximate area. All right, we can't just leave this at 1. Let's do it again. So this time we're going to do with 8 subintervals on a very small interval here. So first let's find out what we are cutting these into, what size. So we're going to go 3 minus 1 over 8 intervals. So our width is 2. Our full interval is 2. So this is 0.25 or a quarter, however you want to look at it. But that's what we're cutting them into. And I've already done that down here. So just like before, if we're going to cut this into 8 pieces, right? Then we go from 1 to 3, and then you cut it in half, and then that in half would be 4, and each of those in half would then make it 8. So each of these makes an eighth. So now how do you find out what the midpoint would be that you have to plug in? So you already know it's 0.25, so that's easy to plug in. It's 1 plus 0.25, so we already know our width here is 0.25. So we're going to add 0.25, add 0.25, add 0.25, add 0.25. So you can find all these x values here, but these are not the inputs. This would be good for left and right hand, but we're doing midpoint. So we still need to find the midpoint. So we do that the same exact way. It's 1.25 plus 1 divided by 2. And so if we plug that in, alpha y, you're going to get 1.125. So 1.25 plus 1. Remember, we're just finding the average. It's just midpoint formula. Divide by 2. 1.125. Now, we only need the first one. That's 1.125. And we can actually use now the table function in the calculator to find it. This is where this would be a lot easier. So if we plug this function into our calculator, and we'll use the table function. So hit pause and do that now. So again, I always like to graph it first. So we have our e to the 1 over x. We go to our window and we go from 1 to 3. And then again, it's zoom 0. Zoom 0 just fits the y values for it. So it gives you a nice quick graph. So there's our function, our graph. You can see it here. Now this one's all the way down to 0. So you can then go back to your window, make your y min 0, and then hit graph, and you'll get the picture like I have. And you could even go back in to your window and then now do your x scalar. So our change here is 0.25. And so now you can see all those little marks like I had before. We have 1, 2, 3, 4, 5, 6, 7, 8 subintervals. So it checks for it. Now hitting trace and then inputting each of these is going to be a lot of work. So it's best to just go second, table set. Our first one is at 1.125. And our delta table is our delta x. So 0.25. And then that way, when you go to your table, it will now actually list all of the different values. So you have 1, 2, 3, 4, 5, 6, 7, 8 of them to input because we have 8 subintervals. So we're going to write all of these down now in our F's. So you're going to hit pause and do that now. Okay. So we end up with this, and I recommend if you have an even subintervals or even non-even, to line them up in groups like this, so that way you can verify that you have 8, that you have your 8 subintervals. If you put them in a line, you do have to count them, and then also see what you start with, see what you end with, and then count down by 8. So 1, 2, 3, 4, 5, 6, 7, 8. So you can see we end with what we're supposed to. Now these are the y values, the outputs. So all we have to do now is write these in replace of these. So hit pause and do that now. Okay, so now that we have them all written down, all we have to do now is calculate what this is and then check with the Desmos graph to make sure that it's correct. So if we input them all in, we get 14.061. Just erase that, put 0.6. There we go. Times our 0.25, because remember these are very, very thin. They're 0.25 width, not very, very thin, just thin. And then put that together, multiplying it, you get 3.51525. So all you have to do is hit the times button, and then and it'll give you the actual answer. Now, if we check our Desmos graph, I've plugged everything in, and we get 3.515. And so you can see this one is actually an underestimate as well. So we would have a positive error in the actual answer. All right, so again, the way you want to always remember these is that you're just making a rectangle and that you have a height which is f of 1.125 for this one rectangle, and a width of 0.25. So all you're doing is doing height times width, height times width, height times width, height times width, all the way across. So it's really just add up all the heights, multiply it by the width, which is 0.25. All right, that's midpoint.